Everybody. Okay, so today we're going to look at closures of set of functions. So the idea, so we saw sentential logic so far, and there are some definitions where we say, oh, the set of terms is everything you can build like this, and when we define the evaluation function, we say, oh, we define it by recursion using the previously defined values in the smaller terms. And that all makes sense. And then I guess intuitively, it should make sense why that's okay. But we're going to be doing that kind of definitions more often in what's coming up. So it'd be good to formalize exactly what we mean when we say T is a set of all, or the terms are everything that can be built using these operations, but nothing else. All right, so that's what we want to see today more concretely, and how we can apply induction to prove things on these kind of terms or whatever we build, and how we can apply recursion to define functions on these things that we build from the bottom up. So okay, here's the setting. The setting is that we have a set U. It's a big set. And we have inside the set U a small set B. And we have a bunch of operations that go from U to itself, and another operation G that goes from U to itself, maybe another one H. And these are operations that take some elements from, they may take one element from U and go to another element of U, or they might take more than one. Yeah, so for instance, we could have that F has maybe two operations, F and G, and that F goes from U times U to U, and G goes from U to U. When we say operation, we don't mean a function. An operation can take many inputs, right? And we want to define what does it mean to take the closure of this original set B and the functions that belong to this family of functions F. Another way of saying the same thing will be, we want C to be the set generated by F starting from B. Okay, so C is generated by the function inside F, starting from the set B. So we're going to look at two definitions, one that we call top-down and one that we call bottom-up. And then we're going to show they are the same. But then they both give you different intuition of what's going on. And in some proofs, it's better to use one, and in other proofs, it's better to use the other one. So it's good to have both definitions. So the one from the top down, so we need a couple of definitions. So we have a set S that is a subset of your big universe U. We say that it's closed under the functions in F, closed under F, if what? If, what do you guys think? If for every function F that belongs to the family of functions that we have, and for every tuple in S of the right length that we can apply F to, because F, remember, takes many inputs. F of S also belongs to S. Okay? So that means that if you are, this is U and then you are in S, and you apply F to the things in F, you stay inside. So when you apply the functions in capital F to things in S, you always stay inside S. Alright, so S is closed under the function because when you apply it, you cannot leave the set. Okay, so that's what it means to be closed under a family of functions. That if you apply them, you stay the same. And another one, we say that is inductive. Set is inductive if it's closed on one side, and also it contains our B, our base elements. Okay, and so last we define C star. This is the set that we want to look at it. It's going to be the intersection of all inductive sets. Okay, so C star is the intersection of all the s's, such that s is included in U and s is inductive. Put them all, take them all intersection, and then so that's the set we want. That's the set that we're gonna call the set generated by f starting from B when we define it from the top down. And okay, so let's look at a couple properties about this set. First is that it's inductive. So that means that it's closed and it contains B. Well, B belongs to all the inductive sets because it was part of the definition of being inductive. So that means that it has to belong to the intersection too. If it belongs to all of them, it belongs to the intersection. Okay, so why is that C star is closed? Well, if you take a tuple, let's call it C bar in C star and F in the family of functions, so that's the number of the number of inputs in little f is the same as the length of the C. We want to see that f of C bar belongs to C, right? That's why we want to C star. If we need to show that it's inductive and closed in particular, so then we need to show that it belongs to all inductive sets. So if we take as inductive, then we have that C that belongs to C star is a subset of S because C star is the intersection of all the inductive sets. And therefore, since S is closed, f of C belongs to S because S was closed under all applications of these functions f. But then this is for every S. This is for every inductive S, right? So that means that f of C belongs to the intersection of all the S's as inductive, which is exactly C star. Yeah, so pause that, go through it slowly and see if you can understand all the steps of why intersection of all intersection of a lot of all the closed sets is closed. Good. So S star is inductive, and S star is just the smallest inductive set. Well, that's because we are taking all the inductive sets and we are intersecting them together, and so it cannot be anything bigger because you are included in all the sets you're intersecting, and it's inductive itself. So there is a smallest inductive set. That's the one that we call the set generated by F starting from B. Okay, so the smallest thing that is closed and contains B. Very good. So that's definition number 1 for set generated by F, or the closure of F. Now we want to look at the definition that we call from the bottom up, right? So this was from the top up. Why do we call that one from the top down? If you take U itself, like the whole set, like the whole universe is inductive. Try to prove that why that's the case. Should be easy. And so that means we are starting from things up that are bigger than your set C star, and C star we're going down and kind of getting to the smallest possible inductive sets. That's our C star. That's why it's from the top down. Now we want to build from the bottom up. And how are we going to do this? Okay, so we have our set universe U that is big, and inside there is a little b that we want to include all these elements. We're going to start just from those elements. And then what do? Then we apply the function, the functions in F to this little c, right? So to C1. So we to all the elements that we have there, to the elements on B, we apply the functions. That's just once. And we get a slightly bigger set, right? So we take all the things you can get by applying any function in F and any tuple that we already have. Apply the function to the tuple, we get new things, and we put them in C1. Then we do the same with C2. We take all the things that we had in C1 and all the possible functions, and we apply the function to the tuple, and we get new things. We put them in C2. Oh, actually we should add here C0, and we should add here C1, because we want to include the previous guys too. We want to not just the ones that you get from the functions, but also the guys that we had before. union C0, union C1, and you keep on doing this. Every step, whatever we have so far, we include, we apply the functions to those elements and we get a bigger guy. And at the end, we do this infinitely many times, and then we take the union of everything bigger. Okay, so the picture will be something like this. You start with a U, here is your B, the starting elements, and that's gonna be our C0. And now we take all the elements inside here and we apply the functions in our family, and we get a set C1, which is by applying the function to this set. So essentially the functions go from here, from there, and now we get a new set. And then we apply the functions again to the things that we have here, now in the new set, and we are going to find new elements, and that's going to be our C2. And then we apply the functions again, and that's going to be our C3, and we keep on repeating this until we end up with, let's do it in red, C under star. So it's a union of everything. You start doing this, everything you get at the end, that's we call the C star, but with the under star. And then we also call this the closure B under F. So we're calling them the same thing, so they better be the same, right? Let's look at a couple of examples to see how this works. So, for instance, suppose, example number 1, suppose that U is a set of all real numbers. Okay, so all real numbers. And B contains the element only 0. And F contains only one function, in this case. And this function, what this function does is it takes an element x and returns x plus 1. Okay, so what is the closure of B, so only 0, using the function f plus 1? So let's do a little picture. So if here is the real line, and then right here is 0, when you apply f, you get to 1, you apply f, you get to 2, and then to 3, and then to 4, and to 5. So the closure of f of this function under the closure of 0 under this function, the C star is going to be the natural numbers, right? So we start applying f more and more and more and more, we're going to end up with all the natural numbers. And the natural numbers is inductive because whenever you have a number, you have the next one. So it's closed under f, and it contains 0, so it's an inductive set. And it's not hard to see that it's the least inductive set. You couldn't have a smaller set that if it has one, it has the other one, right? By induction. Let's look at another interesting example, which is the well-formed formulas of sentential, logic that we saw so far. And so in this case, what is going to be our setting? So U is a set of all the symbols, all the strings that you can build with the symbols. Let's remember all the symbols. You had all the variables, A1, A2, A3, etc., the connectives, and the parentheses. Yeah, so those were all the symbols that we had, and now we look at all the strings which had those symbols, right? So this was the symbols, A1, A2, all the variables, and then and, or, implies, if and only if, not, parentheses, parentheses, all these guys, and strings you can build with these guys. So that's U, all the possible strings you can build, the ones that make sense and the ones that don't make sense. Okay, so what are our starting symbols, our starting well-formed formulas is the variables. The variable symbols by themselves, they were well-formed formulas. You just put them by themselves. It's a one character. It's a string with one character, just the variable symbol. And those are our starting symbols and starting formulas. And now we build the other ones from the variables up by applying the connective. So we have a bunch of formulas. So we have our family of functions is going to contain a bunch of formulas, a bunch of functions, f not, f and, f or, f implies, f if and only if. And what do these functions do? So f not apply to a single object, string in U, something in U, right? So these functions go from U to U. Let me just write that down. This one goes from the set of strings to the set of strings, and when you apply to a string phi, it returns a string not phi. F and goes from the set of pairs of strings to the set of strings, and when you apply to two strings, you return the string that contains a parenthesis, then the string phi, then the character and, then the string psi, and then the character for parentheses. Okay? So you apply f to these guys, and that's what you get. And then the same for the other ones. No, f, you guys can guess, f implies, f or, f if and only if. They all go from U times U to U, and they do essentially the same, but with the corresponding symbols, right? So when you start from the variables and you apply this formula, let me move this up for a second. You start from the variables and you apply all these functions, you're gonna end up with all the formulas, and you're gonna end up C star is a set of well-formed formulas. Make sense? Good. Okay, so let's see why they are the same. So here are the two definitions again. I just wrote them again. So C star on top is the intersection of the inductive sets. C star on the bottom is the union of these smaller sets that we're building one step at a time. And we want to show that the intersection of all these sets and the union of all these ones, they just meet exactly at the middle. And we get one set that is a closure that we want. How will you prove these guys? So this is, we need to prove two inclusions, right? We need to prove C bottom star included in C top star and C top star included in C bottom star. Okay, so let's do whichever you want first. Let's do, I don't know, this direction first. So that means we want to show that each guy in this intersection, so I need to show that Cn is a subset of C star for all n. Yeah? Because if all of them are a subset, then if each of them is included in C star, then you're gonna get that this whole thing is included in C star, the whole union. So why is that? Well, you prove it by induction. On n. And that's pretty simple. C0 is just B. That is, of course, a subset of C star because, well, because C star is inductive. Essentially, the main property about C star, the C top star, is that it's inductive. And it's the least inductive set. So if you want to show that something is a subset of the least inductive set, essentially what you're showing is that it's a subset of all inductive sets. So that's essentially the only property we're going to use. Is that we're going to show that all these Cn's are included in all inductive sets. And then if we know that Cn is included in C star, since C star is closed under the functions, all the functions in capital F, when you apply the functions to all the guys in Cn, we get that Cn plus 1 is also included in C star, right? Because when we apply the functions, we stay inside. So that's what we need to show. Let's now look at the other direction. Now we want to show that C star is a subset of C bottom star. So in the previous one, we used the fact that this C top star is an inductive set, and that's all we used. Just because it's an inductive set, we show that C little star is included in C top star. But now we need to use the other part of the definition, that is the least one, right? So we need to show that it's included in something, so we need to use the fact that it's somewhat small. And that's the part of the definition that says that it's the smallest inductive set. So one way to show this is to show that C star is an inductive set. If you show this one, C bottom star, so we claim it's enough to show that C star is inductive. Right, if we show that C bottom star is inductive, then since the other one is the intersection of all the inductive sets, it has to be included in it. Alright? So be included in C star, yes, that's easy because we know that C0 is just B and then we started from C0, right? So C0 started, so it's included in there. And now if we have a little tuple, let's call it something else, let's not little c because too many c's. Let's call it x belongs to C star, so I need to show and f belongs to capital F. We need to show that f of C belongs to C star, right? That's what we need to show if you want to show that C bottom star is closed, that is closed under the functions. Okay, so why is that? Well, it belongs to here, so and it's fine. It's a tuple, so it has only finitely many elements. And this guy, let's remember what this C bottom star is here, is a union. It's a union of things, right? So if you belong to an infinite union of things and you're a finite tuple, you must belong. You must show up somewhere in the way. No, these CNs are getting bigger and bigger and bigger and bigger. And if you're inside there, inside the whole union, you must show up somewhat in the way. So this one belongs to Cn for some n. But then f of C belongs to Cn plus 1 because Cn plus 1 was defined to be everything you get by applying f to the things in Cn. And that's a subset of C star, by definition of C bottom star. So you get that when you apply F to C, you stay in C star. So that shows that our set C star is inductive as we wanted. Yeah. So that's the proof of why that's inductive. Okay, so pretty good. So now we have these two definitions of the closure of a set of a set B under a bunch of functions that we call capital F. It looks like a pretty robust notion because we're going from the top and from the bottom. We'll see how we apply induction and recursion in the next video. See you guys next time.